Welcome to Lesson 7 of Applied Physics. This lesson covers models, distance, displacement, speed, and velocity. In this lesson you will cover the following objectives. State what a model is, as well as state the necessary aspects of a useful scientific model. Define the terms distance and displacement, as well as be able to state the difference between these two terms. And define the terms speed and velocity and the difference between the two. What is a model? A description of a physical system intended to capture the essential aspects of a system in a simple form so as to be describable either mathematically or conceptually. A model is a way of thinking about something. It may be pictorial, verbal, physical, or mathematical in form. When a scientist is exposed to a problem, these are the classic steps which they take to solve the problem. This is usually called the scientific method. This method has an internal loop in which the scientist continues to make observation, modifies theory, uses the theory to test new predictions, and the process continues. In a field such as wind technology, you will oftentimes be faced with situations where understanding and practicing these skills will become a necessity, and your employer will be glad that you can proactively solve problems before they arise. The well-known particle physicist Richard Feynman once said, "Physics is a game. Any number may play. The object of the game is to discover the rules of nature. The playing field is the entire universe. Any device, physical, conceptual, or computational, can be used. Players may score points but can never win. The game is never over. Players score points by discovering a rule of nature. The greater the number of phenomena explained by a proposed rule, the greater number of points awarded." The following statement by Crumit and Western describes the essential elements of a scientific model, as well as describes the difference between a hypothesis, a theory, and a law. Here are some important aspects of a scientific model. A useful scientific model must do the following: explain observed events, predict future events correctly, and be testable. A valid scientific model must have all of the elements stated on the previous page. A possible model might be: people who disappear in the Bermuda Triangle are abducted by aliens. This is not a good scientific model because it does not have all of the necessary elements. Aliens? This model certainly explains observed events and predicts new ones. If aliens abducted people from the Bermuda Triangle, they certainly would disappear. This model, however, is not very testable. Sure, you can go out in a boat and see if any aliens abduct you. If they abduct you, you can't come back and tell us what happened. If they don't, well, it just wasn't the right day, because they don't always come back and abduct people. They only do it when they feel like it. They must not have felt like it. Because this model lacks one of the three necessary elements, it is not considered to be a valid scientific model. Notice that in the diagram showing the important aspects of a scientific model, the loop back for further testing is always present. We can never say when a model will work 100% of the time. There could be situations or conditions under which the model would fail that have not yet been tested. On the other hand, once a model fails a test, we can say that model won't work 100% of the time. We are going to spend the next few lessons modeling the way that certain aspects of our world work. Along the way, we must keep in mind that our models describe the way the world works. This is the foundation for physics itself. When there is a discrepancy between the way the world works and what our model predicts, the model loses out. Many of the models we come up with will have restrictions or conditions that must be met in order for the model to describe correctly what we observe. We must be ever mindful to remember these restrictions so that we do not apply a model in a situation where it is not valid. Be conscious of your assumptions, or you could be wrong with your analysis. Human nature is such that when we assume we know how to do something, we perform the act without much thought about the assumptions we make. History is replete with thousands of examples of what happens when people don't challenge assumptions. We now begin our study of kinematics, the study of motion without regard to the cause of that motion. We will begin by looking at motion that occurs along a single straight line. This is the only type of motion we can describe uniquely. We will model more complicated motions by using combinations of motions along single straight lines. Before we can fully begin developing models, we must first address the fact that terms in science and engineering are used with certain specific meanings. When a term is used in science, the certain specific meaning that is associated with the term is assumed to be meant. There are terms that you have quite probably used interchangeably in your life that do not really mean the same thing. Put another way, terms in science may have different meanings than the connotations these words might have had in your everyday life. At times, these differences may seem a bit like a game of semantics. Assuredly, it is not. While the differences can be subtle, they can also be significant. With this in mind, we must go back and make some distinctions between terms you might view as being the same. Then we will be able to move forward with our study, or as Yoda said to the young Skywalker in Return of the Jedi, "You must unlearn that which you have learned. Only then can you become a Jedi." We now begin by distinguishing between the terms distance and displacement, and between the terms speed and velocity. This figure shows the distance traveled between two incurable romantics on Valentine's Day. As you can see, it doesn't matter which direction you take as long as you measure the length of the path to get there. Alan and Eve are both displaced from the same starting point, West Gate, which is measured by the same magnitude and same angular direction to their final position, East Gate. However, Alan's path was far different than Eve's direct path. Eve traveled a much shorter distance to reach the same displacement as Alan. These terms and their differences are essential in understanding one-dimensional motion. Suppose that you have 2 points, A and B, that are 3 meters apart. If you were to start at A and go to B, you would travel a distance of 3 meters and your displacement would be 3 meters to the right. If you were to start at B and go to A, you would travel a distance of 3 meters and your displacement would be 3 meters to the left. So it would appear that the distance traveled by an object is simply the magnitude of its displacement during the time interval. However, consider the following trip. You start at A, go to B, and then turn around and go back to A. The distance you have traveled is 6 meters, 3 meters from A to B, followed by 3 meters from B to A. Your displacement, however, is 0 meters to the right. The distance from the point that you end up at to the point you started from is 0. Here, the distance traveled is not the magnitude of the displacement. The moral of this story is to never take shortcuts. Always go back to the original definitions of the terms and apply them correctly. Only then can you be sure to avoid the traps and pitfalls that can slow your progress in this course. Take a minute to review your instructor's model on distinguishing distance and displacement. We will use this symbol for distance, or this one for distances along other axes, and this symbol for displacement, with the other analogous symbols for the other axes. The arrow over the symbol for displacement indicates that there is a direction associated with this quantity. More simply, it indicates the quantity is a vector quantity. The text tells you to specify direction with a plus or a minus sign in this chapter only, and then scolds you for doing so in every other chapter of the book. We don't believe in starting bad habits that you have to break. For this reason, we want you to specify directions on vectors the same way as we will for the entire rest of this course. How do we do that? Glad you asked. Let's go back to our example of walking from A to B. We indicated the direction of the displacement using words 3 meters to the right. We could also use the associated unit vector for the x-axis, 3.0 meters I hat. As a reminder, the unit vectors associated with the 3 rectangular coordinate axes are shown here. So, for this chapter, just like for all of the chapters that follow, we are not going to consider plus or minus as sufficient to indicate a direction. You must answer which axis as well. When solving problems for this class, the standard convention for coordinate axes will be used. To the right will be the positive x direction. To the left will be the negative x direction. Up will be the positive y direction, and down will be the negative y direction. You may use any sign convention you wish. However, if you do not indicate your choice for sign convention, the standard convention will be assumed whether you intended it or not. Review this information on speed. Review this information on velocity. Notice the arrows on the golf ball. They represent direction, an essential part of the definition of velocity. This is interesting to note that if you do an internet search like Google or Bing for an image of the word velocity, most of the images show speed or magnitude, but rarely do they include the direction or compass with the image. This is probably why we have a difficult time breaking the misconception of these terms, because common language doesn't define the words exactly enough for the scientist. This figure shows a speedometer and a compass, which would be great for defining your velocity. The additional altimeter would be even a better method to add a dimension to your description of position and velocity, aka your state of motion. Recall that average speed is a change in distance divided by a change in time, while average velocity is a change in position, the displacement, divided by a change in time, including the direction of the displacement from your point of origin. Again, be careful to define your terms properly. Let's return to our example from the discussion about distance and displacement. Suppose you walk from A to B in a time of 4 seconds, and then from B to a point halfway between A and B in a time of 3 seconds. What is your average speed for the trip? What is your average velocity? Notice the average velocity has an associated direction of I hat with it. This means positive x direction or displacement. One would wonder, can you do the arithmetic average of these two terms to get an average of the average speed? Would that be the average speed for the entire trip? Take a look at the next page to see why this is a bad conclusion. Notice that if you take the average of the average speeds for the two intervals shown here, you do not get the average speed for the entire trip, 0.643 meters per second. Again, you must always go back to the definitions of these terms and apply them the way they were developed to get useful information. Try this problem on your own. A person drives 30 miles per hour for 1 mile. How fast must this person drive the next mile in order to average 60 miles per hour for the 2-mile trip? Remember, you must take care to only apply a model in situations it is designed for. Always apply the definitions related to distance displacement and speed velocity to get correct information using our model of motion. Your instructor will give you assignments for the next part of the course. Hopefully, you have a better understanding of the terms associated with one-dimensional motion. Kinematics is a foundational piece of physics that cannot be ignored if your study of the topic is to be successful. In this lesson, you cover the following objectives.